Hello everyone. In this chapter we want to talk about simulation. So far all the parameters and all the decision variables that we had was deterministic. That means we were sure that this is the correct value for the parameters that involved in the decision making. But in this chapter we want to talk about the cases that decision variables are not known, but we have some estimation about these decision variables, and we are going to introduce a method that we call Monte Carlo simulation method. So in this case, in many models we have the case that value for one or more independent variables are not known. Basically we are not certain about the value. So if we don't have certain value for the input parameter, therefore the dependent variables also is going to be uncertain. So in this case, when we are not sure about the value of some independent parameters, we use simulation. So simulation is a tool that we use for basically applying this kind of uncertainty. So let's start by a simple example. Let's say we have a company ABC, which is a startup in the medical devices, and they want to analyze their profit for the first year. So they have identified that their profit is a function of the selling price per unit represented by P. Then they have the administration cost represented by CM, then the labor cost represented by CL, and the parts cost per unit represented by CP, and the demand by D. So if we want to calculate the demands, because labor cost, part cost, and selling price are the function of the units, it depends on the number of the demands that they have, and it's assumed that all the production is going to be sell out. So the profit is P minus CL minus CP times D minus CA. So this is a function that we have. Now the company has done some study, and they got some numbers that their administration cost for sure is going to be $1 million, and their selling price is $250. So these numbers are fixed and constants, but they are not sure about the three parameters that left: CL, CP, and D. So these are the three values that they don't know. Basically they are dealing with one function, the profit function, which is two numbers are known, the rest is unknown. So CL, CP, D are the variables that we don't know, and we are not sure about their value. Company has done some more analysis, and they got estimation about each of these parameters. They know that the demand for the product is between 0 and 30,000. The labor cost is somewhere between 40 and 44, and the price per part cost is somewhere between $80 and $100. So they are not sure exactly, but these are the values that they have. The easy way that we can consider is two extreme cases. One of them is a worst case scenario. That means we pick up the numbers that represent the worst possible scenario that we can see. So in this case, because the worst case that can happen is demand be 0, and we have a highest cost for the parts and the labors. That means CL and CP becomes the highest value. That means CL becomes 44, CP becomes 100, and the demand becomes 0. In this case, profit becomes 250 minus 45, the labor cost minus 100, the parts cost times 0, the demand minus $1 million. So the profit that they are getting is minus $1 million. That means they are losing this much value. But how about the best case scenario? What happens if we be optimistic and consider the best possible case that happens? For example, demand is $30,000. The cost of the labor is a minimum level, and the cost of the parts is a minimum level. That's the profit. That's going to be highest profit for this company. So in this case, the best case scenario is 250 minus 40 times minus 90 times 30,000, which is a demand, minus $1 million. In this case, the company is making $2,600,000. So based on this analysis that we have, the company makes something between minus 1,000 and $2,600,000. So this is only information that we can get based on the worst and best case scenario. So this doesn't provide much information for us. The way that we can do is we do more analysis, and what we call it, we do more tests or more trials or simulation to get more information about the case. So we need more information. For example, this demand, what is the distribution of this demand? How and what is the likelihood of these values? For example, what's the distribution of the demands that we have? How about the labor cost and other parameters that we have? So we need to know more about likelihood of each of these values that we have for these parameters. Now let's suppose that the company has done more research and they came up with the following information. For example, they know the demand is a normal distribution, which is the mean is 15,000 and the standard deviation is 5,000. So we have something like this. So this is a normal distribution. The mean is 15,000 and the standard deviation is 5,000. So this is a bell curve shape, and it starts from almost zero, but we have some values that they are in the negative part, and this is a very well curved bell curve normal distribution that we have. And then they also come up about the CL, that as you remember, CL is between 40 and 44, and they estimated that the probability distribution of this factor is there is a chance that 40 happens by 1%, 10%, and 41 happens by 20%, 42 happens by 40%, 43 happens by 20%, and 44 happens by 1%. So this is the discrete distribution that we can see for this labor cost. And for the next parameter that we have is the part cost, and this has a uniform continuous distribution, which is the value is between 80 and 100. So minimum is 80, 100 is the maximum value, and any value between these two values, between 80 and 100, has an equal chance, and all of them have the probability of 1 over 20 or 5%. So that's the possible case that each of these numbers that you can see between 80 and 100, they have an equal chance to have. Now the question is how we can do the simulation when we have different kind of a distribution. For example, we have a normal distribution, we have a discrete distribution, and also we have a continuous uniform distribution. How we can use these values in the simulation. So let's start by functions that we have in the Excel. So Excel has a very good function called rand, which generates a random number between 0 and 1, and it technically is not a random function, is not a completely random. This is pseudo random, but that's okay. We can use this random function. So this rand generate a number between 0 and 1 from a uniform distribution. Another function that we can use in the Excel is a rand between. So this generates an integer number between the top and bottom. So we have a bottom numbers and the top numbers, let's say 20 and 50. So both are the top and bottom of this between, and then you are going to get the integer value for this from this function. But when we so if we are, for example, for the CP that we have a continuous value and not all integer, then we cannot use rand between. We have to use a rand function in a way that generates the numbers, any possible numbers between these two values. So the way that we can do is that if we have a continuous uniform distribution, we grab the minimum bound, which is 80 here, and then we compute the length of this distribution. The length is the maximum value or maximum bound minus the minimum bound. So the difference between 100 and 80 becomes 20 times rand. So this is a way that we generate any value between 100 and between 80 and 100. So rand could be 0 to 1, and we can possibly generate any kind of numbers that we have. So this is the way that we deal in the simulation. We generate a uniform. We generate values for the uniform probability distribution. Now the second question is how we can use the random numbers for the discrete probability distribution. In this case, for the labor cost, which has a discrete distribution, discrete probability distribution, we can use a rand and VLOOKUP at the same time. So the way we do is that we order the values from smallest value to the highest value. So we order in the ascending order, then we write the probability associated with each value. Then we write the cumulative probability distribution. So the cumulative probability distribution is just we add up these values. 0.1 is for the first value, the cumulative probability distribution is 0.1. For the second one is we add 0.1 plus 0.2 becomes 0.3. So this is a cumulative probability of this one. Basically we add this value and this value. 0.2 plus 0.1 becomes 0.3. So we are cumulatively adding the values, and it should increase gradually. So we calculate up to this point. Then the next point is 0.4. 0.4 plus 0.3 becomes 0.7. 0.7 plus 0.2 becomes 0.9, and 0.1 plus 0.9 becomes 0.1. Now we use this cumulative probability distribution as the upper bound, and the lower bound is we move one level back. That means for the first value we have the lower bound of 0. For the second one we copy the cumulative value of this value basically. So this value is one step behind the upper bound. So this becomes 1.1, 0.3, this one 0.3, and then the second one, the next one becomes 0.7 and then 0.9. Now, we use a rand function. If the value of the rand function is between 0 and 0.1, value should be 40. If the value of the rand function is between 0.1 and 0.3, the value in the trial, in the simulation, is 41, and so on. So we use a rand function to generate these values, and then we can use a VLOOKUP to find the value that we can use in the simulation. So this is a way that we can use for any discrete values, that any discrete probability distribution that you can see. But for some of the probability distribution for the well-known probability distribution, we have Excel functions that you can use it. Also, we have posted the documents on the Ch12, so you can find and look that up. So the next parameters that we have is the demand, and the demand has a distribution of the normal, which is the expected value was 15,000 and the standard variance was 5,000. So this is a normal curve that we already saw. So the mean is this value, standard deviation is 5,000, so between these two values, and this is a very bell curve normal distribution. To generate a value from a normal distribution, Excel has a function. The function is normal in, so norm.in means inverse of the normal, and you can put the random value, so and point the mean of this distribution and the standard deviation of this distribution. So this means if you put rand, which is between 0 and 1, you are going to get a value from this function. Let's say rand is 0.6, so 0.6 means all the area up to from minus infinity to this point is 0.6, and the value for this function from, if you put rand 0.6 in this function, norm.in 0.6 mu equal to 15,000 and standard variance is 5,000, you are going to get 16,267. So this is a way that we generate a random value from this normal distribution. For other continuous functions, you can check the file that we posted on the Ch12. Now let's do some simulation, how we can do the Monte Carlo simulation in the Excel for this case, for this company. So we had some parameters. We had the parameters that was the selling price, we had the administration cost, we had the lower the cost of the labors, and we use a VLOOKUP rand. So if you check it, so this is an area that we have a rand function and the area of these numbers, and this is the index that it chooses, so the values are here and it's an exact match. Then we have the unit cost, parts cost, which is continuous uniform distribution, and it is between 80 and 100. So this is a lower bound plus 100 minus 80 times rand. So this is the way that we use this function. And demand. So demand is most of the time is an integer number. We can use in round numbers after generating the numbers from the normal distribution. So this is norm.inverse. This is a rand, and the expected value of 15,000, and standard deviation is 5,000. And then we can round this. So this is a first number is numbers that we got from the normal distribution, and then the number of digits that we want to. So this is the way that we can do. And the profit is basically P minus CL minus CP times the demands minus the administration cost. So the simulation is just doing multiple time of generating a random number. So most of the time the number of the iteration that we have should be somewhere around, it should be a big number like 1,000 but or 2,000, but in this lecture we just show 100 iteration that you can see just how this simulation works. So we have the 100 iteration. Then we have the p-values. Even though these values are constant, we just want to show how this simulation works. Then we have the cn, then we have the cl, so you put their values here. Then we have the cp, then we have d, which is the demand, and then we have the profit. So to do simulation and do all of this 100 iteration, you select all of these cells, so you select from the top to the bottom all of this, and then you select the data tab, and then what if analysis, and from the what if analysis select the data table, and then select the column input cell and click in every place, and then click OK. So you're going to see some values are generated. So this is the purpose of simulation. This is the first step that we do. So you set up the parameters, you find the, if they have a specific distribution, you generate the random numbers here, and then you create a table and put the random number for each cell that you have. So again, in the data, what if analysis data table, you put in the column input cell and then click on this area, and then so this is the way we can do it. Now, after doing simulation, we need to do some analysis. So let's have the summary of the simulation. So first we need to find out the input and output parameters and find out which one is a deterministic and which one is a non-deterministic one. For those that they are non-deterministic, we have to use a proper randomization method. So if basically how we can generate a value for those non-deterministics, and then we run the simulation. So the way that we show, there are some these are some of the well-known probability distribution that we can use. Binomial. So if you want to generate a binomial value, you can use the function called binom.inverse, np, and rand. So n is the number of the replication, p is the probability of this binomial, and so on. So you can find the details. This is the normal that we already saw it. We have the exponential function, we have the triangle function, so you can find the detail in the documents that we have it. Then we have the continuous uniform, so this is the way that you can generate it. If the integer uniform, we can use this in ramp between and provide the minimum value and maximum value for this distribution. Then we have so many other distribution that we can find on the basically the document, also in the help of the Excel. So once we have done the simulation, we need to do some analysis. The analysis should be what is the best case and the worst case, so as well as the descriptive statistics like what is the average, what is the median, standard deviation, and how many times we have a positive, how many times we have a negative, what's the probability that we get a negative basically profit, and so on. Also, we can compute the frequency and percentile distribution that we are going to see, and then the confidence interval. So let's do the first basically descriptive analysis and the frequency. That they are very helpful to analyze the situation. For the frequency and percentile distribution, first we need to compute the mean and standard deviation of the simulation, and then we can create the mean of the frequency. So we need to compute mu plus z sigma. Sigma is the standard deviation of the sample, mean is the mu is the mean of the samples that we can compute. When for the value of the z, put -4 to 4, and it increased by 0.5, so -4 minus 4, minus 3.5, minus 3, and then so then you use the frequency function in the Excel and make sure that when you are use Control Shift Enter all together. So we are going to work on this one in a minute. Okay. So this was the file that we just worked on, and it has 100 replications. So let's do the minimum, maximum, average. So the mean is minimum value, and we know the function that we can use is mean, and the range of the numbers that we have is this much, so we can use the $sign for all of this. So then this is a minimum, then the maximum is a max function, then we can use average, so then the next one that we need to is the standard deviation. For the standard deviation, we use standard deviation of the sample, so STDE, and then all the values that we have. So ST population, so this is a mean of the value, this is a standard, and then we need to find the frequency. So in order to find the frequency, we create the z's, which starts by 4 minus 0.3, 5 minus 3, and so on. So we select all of this up to 4, then we create the beans. So the bean is average, plus this numbers times standard deviation. So we reference to these cells, and we select this. Now the function that we can use is the frequency function. So this is, let's say, frequency value. So we select all of this, then we click on the formula bar, equal, and then frequency. So then the values that data array, so the data array is the profit that we have. We select all the values, and then asks for the bean array, which is the beans that we have created. And then once you close the parentheses, you make sure that you click on the Control Shift Enter all at the same time. So you can see when you see the equation there is so one more time, Control Shift Enter, and you can see there is a bracket. That means for this group of the cells that we are applying this function. So you can see the frequency is represented, the number of the values that they are smaller than this value is 0, and for example between these two is 0 again, between these two is 1, and so on. So this means how many frequency of these numbers for each one. And you can see that most of these numbers are in the middle. So the value of the z here represent a kind of normal distribution. For example, we know that most of the time between minus and 2 is enough range to represent the numbers, but covering minus 4 and plus 4 is basically we are making sure that all entire range are covered. So if you plot this using these bars, you can see more data about this value. So select the data, and series name is a frequency. Then we select this frequency values, and for this we can select the value of the pin, and you can see more accurately that what is the numbers, what is the frequency of these numbers. Now if we divide the frequency by 100, which is the number of the replication, we get the probability or percentage of frequency. So let's divide by 100, then and then add up these numbers. So we calculate the cumulative, and this is a cumulative probability, and so basically we are adding these numbers all together, and at the end we should get them 1. So let's plot this one in the another graph. So let's choose this graph and remove all of this. So for the value of the x, we choose the mean values, and for the y values, we choose the probability values, cumulative frequency basically. And you can see there is almost S shape here that is close to normal cumulative probability distribution. So if you update every time, you can see this shape changed a little bit. If you have a higher number of the replication, this shape is going to stay pretty similar. Then you are not going to see much variation. 100 is not enough numbers. You see there is a sharp change here, but if you have a higher number of the replication, then you're not going to see such change, sharp movement. Now other descriptive values that we can have is the count. So we already know, basically we did 100 repetitions, so still count or n is the number of repetition that we can use. So this is count. Then sometimes we need to know the probability that the profit is negative. So here we can use a function called count if. So count if is the functions that counts the numbers, and the criteria that we can use is less than 0. You can choose any values less than 100, 200, and so on. So this counts the number of the elements, number of the cells that their value is negative, and if we divide it by n, then we get the probability of the getting 0, basically negative value. So there is a 8% chance that we get a negative value. And also we want to know how much variation we have for this value. So we can basically use a square of this values times 1 minus of these values and divided by number of the repetitions that we have. So this is basically calculates how much variation we will have for this probability. So these are most of the descriptive values that we can get or compute for the simulation. But there is one more measure that we can get for the simulation, that's frequency. So let's have some numbers, starts from 0.01, then 0.05, 0.1, 0.2, 0.25, then 0.5, 0.75, 0.9, 0.95, and 0.99. So assume these are the values, which starts by basically 0.01 up to 0.9, and let's have one more value, which is 0.99. So here we can find the percentile, which is this percentile means how many numbers, how many of these values are smaller than these values. So basically we select the profit column, and so reference to all this, and the next one is a K. So it means that almost 1% of the values that we get is smaller than 9, or smaller or equal to 91,032. So this is the value, almost 1% of the simulation that we have, they generate profit of minus 9. Basically we are losing 9,000 1,000, and if we apply this value for the rest, so you can see 5% we are getting, for the 5% of the simulation we have minus 362,000 or less. For 1% of the simulation we are losing $54,528 and so on. And you can see 20% of the simulation that we have, they are less than this value, 19,000 and so on. So this shows how many number of the simulation are less than this value. So if let's plot this value on this cumulative and see what happens. So this is basically, let's choose this one as the X values, and then this one as a Y values. And you can see the graph are matching. So this cumulative frequency and this percentile are pretty much similar. So the concept of the percentile means that, for example, for this value means that 5% of the simulation resulted in the 362,000 loss or more. That means we are losing more than this value for the 5% of the simulation. This one says, for example, 50% of the simulation we are getting less or equal to $825,207 or less for 50% of the simulation. So this means basically how much we are getting, what is the percent of the simulations that what is the percent of the time or chance that we get this value or less. Basically, this represents probability of the profit is less than this value, 827k. So this is the value that we are getting by percentile. Now we want to talk about how we can find the lower bound and upper bound for the minimum and the probability of the profit negative. So now we want to talk about finding lower bound and upper bound. So we call it confidence interval. So when we are talking about the profit or mean of the profit, we have to introduce some notations. These notations are alpha, which represent the significance level, and most of the time is 5%, 1%, so that's a small number. Then we have the confidence level, which is 1 minus alpha. Now let's assume mu is the mean of the profit that we get from the simulation, then n is the number of the trials in the simulation that we have, and standard deviation is the standard deviation of the profit that we get from the simulation. Now there is an equation that we can find the confidence interval. So this confidence interval use the mean of the profit that we get and standard deviation that we compute. Also it has some notations. First of all, we use a function in the Excel that called normal standard inverse, and this alpha is a given small number, something like 5% or 1%, and 1 minus half of that, it gives a number from normal distribution. So this becomes a probability, and then you are going to get a number. This number is something around 1.6 or 1.9 depending on the value of the alpha. So basically this generates a lower bound of the mean of the profit, and this side provides the upper bound. Mu is a given that we calculate. This is extracted from the normal standard deviation or normal standard distribution. Then this standard deviation is a standard deviation of the profit divided by the square of the n, which is number of the trials as we have. So mu minus this value is lower bound of the mean of the profit. Mu plus this value, so the plus and negative are exactly the same, so we are subtracting and adding one constant value from the mean, and we are providing an interval, and we are saying that we are this percentage, we are sure that the mean that we get for the profit is going to be in this interval. So that's the meaning of this. So we are, for example, 95% sure that mean falls in this range. So if we do the experiment, this is our mean is going to fall in this interval. Now, similarly, we can compute the confidence interval for the probability of the profit being negatives. The same notation we are using here. We have the alpha, which represents the significance level. 1 minus alpha shows the confidence level. We have the probability p bar, that probability of the profit being negative from the simulation. So the way that we count how many of the trials are negative divided by number of the trials that represent the p bar. Also we compute the n, which is a number of the trials, and here we have a similar equation. For example, we have the p bar, which is equal to mean of this. Basically this is a value that we got for the number of the trials, that they are negative divided by number of the all trials. The same way that we had for the mean, we have the normal standard deviation inverse, 1 minus alpha divided by 2, 1 minus alpha divided by 2. And then the same way we have the standard deviation. Here, standard deviation for this value is p bar times 1 minus p bar. So this represents the standard deviation for the binomial distribution. And then we have the same plus sign here, so p bar minus norm standard deviation inverse. So this value, you can plug it in the Excel and find this value, then basically multiply by standard deviation. So for the example that we had, let's compute this one. So recall that we had the basically we had all of these values. So we had the probability that profit is negative is right now is 0.007. Then we have the standard deviation, which is a multiplication of these two and divided by n. So this is the second step. Now let's compute the confidence interval for the mean. So this is confidence interval, and let's say alpha is equal to 0.05. So alpha is all the time is given, so we assume this is alpha is 0.05. So the lower limit of basically lower bound of confidence interval of mean is mean, which we have it here, minus normal standard deviation inverse. So here normal standard deviation minus half of alpha divided by 2, then multiplied by standard deviation divided by square of n, which is number of the basically trial that we have. So this is lower bound. So lower bound is this value. The same way that we computed the lower bound, we can compute the upper bound. So upper bound is going to be average plus normal standard deviation inverse 1 minus alpha half of alpha times standard deviation, so divided by square of n. So this is lower bound and upper bound for mean of the trials, mean of the profit. But for this p, the probability also we can compute the lower bound and upper bound. So that's it is this value minus normal standard deviation inverse. So here you put a probability and then you got some value, which is most of the time is somewhere around 1.6 or 1.9. So depending on the value of the alpha divided by 2 and multiply by a square root of, we already calculated here, so we just put this value. So this value is a square of p bar times 1 minus p bar divided by n. So this is the lower bound. So that means the probability, this means that the 95%, so basically the interpretation of these two values means that we are 95% sure that mean falls in this range, then for this one the probability of the being negative means we are sure that for 95% falls in this range. And then the upper bound of this one is normal standard deviation inverse 1 minus half of the alpha divided by 2 multiplied by this value. So because every time that we change the trial or simulation is run one more time, we are getting new values, but this alpha is 0.05 and confidence level that we have is a 95%. This value shows upper bound and the lower bound or confidence interval for the mean of the portfolio. This one shows for the probability of them getting negative value. So the interpretation of this one means that we are sure that by 95% that the mean falls in this range, and we are for this one we are sure for 95% that the probability that we get negative profit is fall in this range. So this is basically end of this lecture.